In the middle of the Taklamakan Desert, China just completed drilling the deepest hole in Asia, 10,910 meters straight down into solid rock. That's deeper than Mount Everest is tall. The second deepest vertical hole ever drilled in human history. The project took 580 days. The last 910 meters alone took 300 days, almost as long as the first 10,000 meters combined. At the bottom, temperatures exceed 210 degrees Celsius, hot enough to vaporize cooking oil. Pressure reaches levels greater than the deepest point of the Mariana Trench. China claims they're drilling for scientific exploration and oil research, studying Earth's geological history and searching for energy resources. That's not the whole story. What is China really after drilling the deepest hole on Earth? We've sent robots to Mars and photographed black holes 55 million light-years away. We've mapped the surface of distant planets in detail that would have seemed impossible a generation ago, but we still don't know what's beneath our feet. The distance from Earth's surface to its core is roughly 6,370 kilometers. The deepest hole ever drilled reached 12,262 meters. That's 0.2% of the way down. If you imagine Earth as an apple, we haven't even broken through the skin. Everything we know about the deep interior of our planet comes from indirect measurements. Scientists study how seismic waves from earthquakes travel through rock, and from those patterns, they build models of what might be down there. It's like trying to understand what's inside a sealed box by shaking it and listening to the rattling. The method works well enough to give us a rough picture, but a rough picture isn't the same as direct access. Being able to pull a piece of rock from 10 kilometers down, place it on a laboratory table, and study its exact composition is something else entirely. That's what makes ultra-deep drilling valuable, and that's why the race to drill deeper has been going on for over 60 years. In 1961, just weeks after Yuri Gagarin became the first human in space, the United States launched Project Mohole. The plan was to drill through the ocean floor near Mexico and reach the boundary between Earth's crust and mantle, a layer called the Mohorovičić discontinuity. The idea made sense. Oceanic crust is thinner than continental crust, only 5 to 7 kilometers compared to 30 or more on land. Drilling through ocean floor seemed like the faster path to reaching the mantle. Early test drilling in 1961 successfully retrieved rock samples from beneath the sea floor, which created worldwide excitement. But the project quickly drowned in cost overruns and political infighting. By 1966, the US Congress shut down funding. Project Mohole never reached the mantle. The Soviet Union watched this failure with interest, and in 1970, on the Kola Peninsula in northwestern Russia, they began drilling a hole designed to surpass anything the Americans had attempted. The Kola Superdeep borehole wasn't placed randomly. The site sat on the Baltic Shield, one of the oldest pieces of Earth's crust, where rocks dating back 3 billion years reach close to the surface. Soviet scientists believed that drilling 10 to 15 kilometers down would expose the mantle directly. The first phase went smoothly. By 1983, the drill had passed 12 kilometers. In 1984, at an international geology conference in Moscow, Soviet officials announced they'd reached 12,066 meters. Delegates were taken to the site, shown the drilling operation, and given core samples as proof. Then everything went wrong. When drilling resumed after the conference, the drill pipe snapped at depth, leaving 5 kilometers of steel permanently lodged in the hole. The team had to start over from 7 kilometers, drilling a new branch around the lost equipment. By 1990, they reached 12,262 meters, setting a record that still stands today. But the real value of the Kola borehole wasn't the record. It was what they found on the way down. Soviet geologists expected to hit a transition from granite to basalt at around 7 kilometers depth. That's what seismic data suggested. That's what the models predicted. When the drill reached 7 kilometers, there was no basalt, just more fractured, superheated granite, extending far deeper than anyone thought possible. The seismic models that scientists had trusted for decades were wrong. Temperature was another shock. Predictions said the rock at 12 kilometers would be around 100 degrees Celsius. Actual measurements showed 180 degrees. The heat flowing up from Earth's interior on the Kola Peninsula was far more intense than expected, which meant the mantle was either closer than models suggested, or the crust itself was structured completely differently. The most unexpected discovery was water. At depths where rock should have been compressed into a dry, solid mass by the crushing weight above, the drill found hot, mineral-rich fluids everywhere. This water couldn't have filtered down from the surface. Pressure at those depths would prevent it. The water had been there since the rocks formed, trapped for billions of years. That discovery changed how geologists understand Earth's crust. The deep crust isn't a dry, solid block. It's saturated with ancient fluids that play a major role in how heat moves, how minerals form, and how tectonic forces operate. There was also gold. Below 9.5 kilometers, core samples showed gold concentrations around 50 grams per ton. Industrial mining operations consider 4 to 5 grams per ton worth extracting. Nobody expected economically significant metal deposits at those depths. The Kola borehole proved that every time humans drill deeper into Earth, the planet delivers surprises that contradict what we thought we understood. And now China has drilled to similar depths in completely different geology. Whatever they found down there, it's not going to match what the Soviets discovered under Russia. The Shendi take. One borehole sits in the Tarim Basin, one of the harshest and most geologically complex regions in China. The basin is trapped between the Tian Shan Mountains to the north and the Kunlun Mountains to the south. Summer temperatures in the Taklamakan Desert exceed 50 degrees Celsius. Winter temperatures drop below -30. China started drilling on May 30th, 2023. The rig they built for this project is a 72-meter-tall automated platform capable of handling loads over 900 tons. It's designed to drill up to 12,000 meters and operates with 90% domestically manufactured components. On March 4th, 2024, the drill passed 10,000 meters. State media broadcast the moment live. Engineers and scientists gathered at the site erupted in applause as the depth counter crossed 5 digits. But reaching 10,000 meters was only the beginning of the hardest phase. The final 910 meters took another 300 days, almost as long as it took to drill the first 10,000 meters. At extreme depths, every meter becomes exponentially harder. The drill hole narrows to barely 20 centimeters wide. The equipment must survive temperatures that melt standard steel and pressures that exceed 1,300 atmospheres. One engineer compared the task to driving a massive truck balanced on 2 thin steel cables. The slightest deviation, the smallest vibration, and the entire column of drill pipe can jam permanently in the rock. On February 20th, 2025, China announced completion at 10,910 meters, the deepest vertical well in Asia, the second deepest in the world. So what were they really drilling for? The official explanation is oil and gas. The Tarim Basin holds more than 60% of China's ultra-deep petroleum reserves. Most of these resources sit below 6,000 meters, depths that were unreachable with older drilling technology. Proving that extraction is possible at 10 kilometers opens access to reserves that could supply China's economy for decades. China is the second largest oil consumer in the world after the United States. It's also the largest oil importer. Every year, hundreds of millions of barrels arrive by tanker from the Middle East, Russia, and Africa. That dependency represents a strategic vulnerability that Chinese planners have worried about for years. Every barrel of oil produced domestically is one less barrel that has to be purchased from potentially hostile nations or transported through sea lanes that could be blockaded during conflict. Ultra-deep drilling reduces that vulnerability. But oil is only the first layer of the answer. At 10,000 meters depth, rock temperatures exceed 200 degrees Celsius. That heat isn't coming from the sun. It's radiating up from Earth's interior, a byproduct of radioactive decay in the mantle and residual heat from the planet's formation 4.5 billion years ago. If you can access that heat, you have an energy source that never runs out. Unlike solar panels that only work during the day or wind turbines that stop when the air is calm, geothermal energy is constant. The planet generates heat 24 hours a day, every day, for billions of years into the future. According to estimates from the International Energy Agency, the geothermal energy stored in Earth's crust between 5 and 10 kilometers deep contains 50,000 times more energy than all known oil and gas reserves combined. The challenge is reaching it. Standard geothermal plants tap into shallow heat sources a few kilometers down. Ultra-deep geothermal requires drilling technology that can handle extreme conditions and survive long enough to make the project economically viable. China isn't just experimenting with this technology. In November 2024, they completed a 5,200-meter geothermal well on Hainan Island, punching through 250-million-year-old granite to access deep heat reservoirs. The data from Take-1 feeds directly into expanding that program. Control over ultra-deep geothermal energy means China could power its industrial economy without burning coal, without importing oil, and without relying on weather-dependent renewables. That's energy independence in the most complete sense possible. But there's more. On May 12, 2008, an earthquake struck Sichuan province. The magnitude was 7.9. Nearly 70,000 people died. The quake originated roughly 19 kilometers beneath the surface in a fault zone that geologists knew existed but didn't fully understand. If scientists had better data about stress, temperature, and fluid pressure deep in the crust, they might have detected warning signs. Deep boreholes allow researchers to install sensors far below the surface, where precursor signals to major earthquakes can be detected long before anything reaches the surface. Japan already operates deep monitoring networks, though at shallower depths than what China is now achieving. The ability to place instruments 10 kilometers down in seismically active regions could save tens of thousands of lives by providing hours or even days of advance warning before catastrophic quakes. This isn't speculative science. It's a practical application of ultra-deep drilling technology that directly addresses one of China's most serious natural disaster risks. And there's still another layer. The Tarim Basin shares the same deep geological history as South America, Africa, India, and Australia. These are fragments of ancient supercontinents rich in metals, rare earth elements, coal, and other resources that modern economies depend on. Rare earth elements like neodymium, lithium, and cobalt are critical for manufacturing batteries, electric motors, wind turbines, and electronics. China currently dominates global supply of these materials, but domestic sources are limited, and extraction is environmentally destructive. Geological surveys suggest significant rare earth deposits exist in deep rock formations across the Tarim Basin. If ultra-deep drilling proves that these deposits can be accessed economically, China gains leverage over global technology supply chains that no other nation can match. There are also indications of substantial offshore oil and gas reserves in the Ross and Weddell Sea regions beneath the Tarim sediments, resources that weren't accounted for in earlier exploration because the technology to reach them didn't exist. China isn't drilling one hole and calling it done. Multiple ultra-deep projects are underway across the basin. They're not looking for oil in one spot. They're systematically mapping the deep structure of an entire region to understand what resources exist and how to extract them. At 10,000 meters below the surface, the environment is as hostile as deep space. Temperatures that vaporize organic materials. Pressures that exceed the deepest ocean trenches. Drill bits wear out after penetrating just a few meters of rock. Every meter costs exponentially more than the one before it. The engineering required to operate in these conditions pushes the absolute limits of materials science, automation, and precision control. When a drill string 10 kilometers long starts to vibrate or bend, there's no easy way to correct it. If the pipe gets stuck, you can lose months of work and millions of dollars worth of equipment in seconds. China developed automated systems that monitor the drill's position in real time and make micro-adjustments to keep it on course. They created drilling fluids that remain stable at temperatures above 200 degrees Celsius. They built sensors that can survive being compressed by forces that would flatten a submarine. The technological advances required to drill Take-1 aren't just useful for making holes in the ground. They translate into capabilities for deep-sea resource extraction, enhanced geothermal systems, carbon capture and storage, and any other industrial process that requires operating under extreme heat and pressure. Mastering ultra-deep drilling gives China an industrial advantage that compounds across multiple sectors. So what is China really after? Everything. They're drilling for oil and gas to reduce dependency on foreign imports. They're developing geothermal energy to power their economy without carbon emissions. They're gathering scientific data to understand earthquake risks and potentially save lives. They're mapping rare earth deposits to maintain dominance in technology supply chains. And they're proving to the world that they can accomplish engineering feats that only the Soviet Union attempted during the Cold War. Each of these goals individually would justify the cost and effort. Together, they represent a comprehensive strategy for resource security, technological independence, and geopolitical influence that will shape the next century. The race to drill deeper into Earth isn't just about science, it's about control. Who controls access to deep resources controls future energy supplies, rare materials, and strategic advantages that haven't even been imagined yet. When the Soviet Union stopped drilling Kola in 1990, the project was abandoned. The site today is a collection of rusted equipment and crumbling buildings in the Arctic tundra. But the data from Kola is still studied and cited in research papers around the world. The science survived, even though the empire that created it collapsed. China watched that happen. They learned from Soviet mistakes. They built better technology, automated systems that don't require constant human intervention at the drill site, materials that can withstand higher temperatures and pressures, and most importantly, they've integrated ultra-deep drilling into a broader national strategy rather than treating it as an isolated scientific curiosity. We live on a planet we barely understand. The ground beneath our feet holds resources we haven't discovered, energy reserves we haven't tapped, and geological processes we can't predict. Ultra-deep drilling is how we access that hidden world. China just proved they can drill as deep as anyone in history, and they're not stopping. More projects are already underway. Each new hole is a data point in mapping a frontier that no one has systematically explored. The deepest parts of Earth are no longer unreachable. The question now is, who gets there first, and what they do with what they find? What do you think China will discover as they keep drilling deeper? Let me know in the comments. If you want to see more videos like this, hit the like button and subscribe. Thanks for watching.